Okay, so I can, if you have questions on the homework still, like I can stay for a few minutes after the class to answer your questions. All right. So today we're going to be looking at the effect of multiple wings and dihedral. So last lecture we have been looking at the planform from above, which looks at taper and sweep, right? And at the end we mentioned that when you add taper at sweep, the wing tips are going to get higher angle of attack. So we didn't mention twist, but the twist is really used to counter that. So if you twist the wing so that it's also called a washout, so that like the tip of the wing would naturally have a smaller angle of attack than the root of the wing. I mean, that's common. If you pay attention next time you take a flight, right, you're going to see most of the commercial airlines both have taper and sweep, right? So they actually add a twist to the wing. If you look at the wingtip, they are pitched at a lower angle than the root. Okay, so that's exactly for the reason we discussed in the last lecture, right? When you have taper and you have sweep, unless you add twist, the wingtip is going to add a higher angle of attack, and as a result, a stall first. Okay, so this lecture we're going to be looking at the wing from behind. Okay, so that's looking at the effect of dihedral and multiple wings. So we're going to talk about multiple wings first, but just a review, right? So last lecture we have seen that the lifting line explains the induced drag twice. One time from the far wake behind the airplane, because the lifting line models all the trailing vortices, and you can compute the flow field in the far wake behind the airplane from these trailing vortices, and therefore you can compute how much kinetic energy is there in the vortices, and from the kinetic energy you can compute how much energy per second the airplane has to dump into its wake, right, to sustain the wake. Okay, and from that amount of kinetic energy per second, which is power, right, that is exactly the induced power the airplane has to spend to have the wake having a downward momentum to generate lift. So that's lift-induced power. And if you divide that power by the speed of the airplane, you get the drag. Okay, that's induced drag. So that's the first time the lifting line theory explained induced drag. And we can analyze that purely by looking at the far wake, only considering the trailing vortices. The second time is what we discussed on Monday. So if you look at the effect of all the vortices, not only the trailing vortices, but also the bump vortices. I mean, in this case, in this specific case where the wing has no sweep, you only actually have to look at the trailing vortices. Now, if you look at the effect of all the vortices on the wing itself, on the quarter chord of the wing itself, you can calculate how much does the induced flow modify the free stream seen by the individual cross sections of the wing. So the free stream seen by the airplane actually differs from the free stream seen by the individual cross sections of the wing, exactly because of the induced flow from all the vortices, right? And because the free stream no longer points in the free stream direction of the whole airplane for the airfoil sections, the lift vector on the airfoil cross sections therefore points towards a different direction, slightly different direction from the lift vector of the entire airplane. And in general, it tilts backward. And today we are going to look at a scenario where it actually doesn't exactly have to tilt backward. It can locally tilt forward. But the most of the time, for example, in this example, the lift vector seen by the individual airfoils would tilt backwards relative to the lift vector of the whole airplane. That backward component of the individual airfoil cross-sectional lift, right, added together is the induced drag of the airplane. Okay, make sense? Okay, so we did that a little bit on Monday, and in the homework, you're also asked to estimate the induced drag using that approach. Okay, so we also looked at the flow near a tapered wing airplane. So for a tapered wing airplane, the flow has to be explained not just by one pair of trailing vortices, by one horseshoe vortex, but by multiple pairs. And because of the multiple pairs, some of the pairs, the trailing vortices starts not from the wingtip, but from the inboard side of the wing, right? And the result of this inboard trailing vortex, right? The trailing vortex goes that way. So if we look from above, and as a result, the induced flow of these kind of vortices, right? You have more over here, but the induced flow for these kind of vortices induce the downward flow over here, but an upward flow on the outside, right? So as a result of the combination of these multiple vortices, the induced flow near the tip is less downward compared to the induced flow near the root. And the result of that is it's explained by these pictures. So as a result of that, the lift, unless you have a washout, unless you have a twist, the lift on the tip side is going to be more than the lift coefficient on the root side. So your tip is going to stall first, unless you add a twist to the wing. We also we didn't do any numerical calculation, but in the homework you're going to see the effect of the taper is going to be even more dramatic if you add a sweep. And the reason is that for the swept wing, the inboard vortices, right, going that way, is going to actually have even a more dramatic effect outside, right? So the influence of this leg of the vortex on this point is going to be more if you have a sweep, because if you look at the angles, right, the angle is going from a positive angle to a minus 90 degrees. Compare this to the no sweep case. If there is no sweep, this would be these two would be perpendicular, right? And the angle goes from 0 degrees to minus 90 degrees. So a sweep actually increases how much upwash the inboard vortex induces on the tip section. So as a result, this is a picture of similarly basically the local lift coefficient as a function of the semi-span position. So semi-span position is equal to y divided by half b, right? So this is 0 means I'm at the center of the fuselage. 1 means I'm at the wingtip. So if I have a large sweep angle like 60 degrees, the effect is even more dramatic, where I have a much higher lift coefficient. In this case, almost twice as large in the outboard portion compared to the wing root. Okay. So this is basically the effect of sweep and taper. So today we're going to start looking at the effect of multiple surfaces, and so before we introduce the effect of the lifting line theory, let me just go over the concept of longitudinal stability and a little bit later lateral stability, and then we'll look at how the lifting line theory, how the induced flow is going to modify the stability of airplanes. Okay, so let me get something straight first. If you have a very lightly loaded airplane with a very high aspect ratio, okay, the induced flow by definition is going to be very small, okay? So in these cases, you can actually do pretty well longitudinal and lateral stability without considering induced flow. So I actually don't know exactly what you covered in Unified, but you might be able to actually design everything without thinking anything about the vortices. And the effect of induced flow really comes into picture when you have an airplane that's no longer have very large aspect ratio, or you want to design everything to very high precision, right? So when you are making an airplane that's large and potentially carrying people instead of an airplane just for fun, right? You then have to start considering all the effects that might be small. And we'll see in other cases, if you have a unconventional design, you have to consider the induced flow, even if you design something for fun. Okay. So let's first of all look at longitudinal stability, just to make sure everybody's on the same page. We'll have you come up to the blackboard and do this example. Okay, so let's actually explain all these assumptions in this example. So in the example, the horizontal stabilizer is 20% of the area of the main wing. Okay, so that's a typical ratio. The quarter chord of the wing is 1 meter ahead of that of the quarter chord of the horizontal stabilizer. Okay, and here we assume the lift actually concentrates on the quarter chord for both the wing and the horizontal stabilizer. And next week we'll explain this is not exactly the case, but in this example we'll just assume that's the case. And the increment of lift coefficient per increment in the angle of attack of the airplane, okay, is the same for the wing and the horizontal stabilizer. So if you touched the thin airfoil theory in Unified or elsewhere before, you're going to know that for very thin airfoils and the very small angle of attack, that the same constant, the dCl d alpha, is 2 pi, right? So, I mean, in reality, for real wings, that's not infinitely thin, and even before the wing stalls, this quantity is not going to be too much different from 2 pi. Okay, maybe 10% lower, at maximum 20% lower, but that's roughly, this number is going to be 2 pi. So in this case, let's assume this number is a constant, no matter if you're looking at the wing or for the horizontal stabilizer. By the way, this is the horizontal stabilizer, this is the main wing, okay? And first of all, let's assume the center of gravity, so this thing, is 0.1 meters or 1/10 of the distance between the main wing and the horizontal stabilizer. Okay, you have to answer what is the proportion of lift among the main wing and the horizontal stabilizer at steady level flight, which means the airplane is not pitching up and down, it's not going up or down. Okay, and what is the proportion of lift coefficient? Okay, then upon a small increment in the angle of attack, how do the proportions change? The proportions means the proportion of lift coefficient and also lift itself. How do these proportions change? And then, if you figure out how do the proportion of lift change, you have to figure out what is the resulting moment around the center of gravity, right? The resulting moment, you have to combine the moment of the main wing and the moment of the horizontal stabilizer. And then answer exactly the same question if the center of gravity is 0.1 meter behind the quarter chord. Okay, please come up and do these questions. And once you have a sense of the result of this, we'll look at how does lifting line theory, how does the induced flow modify the answer to these questions. Where is... Go. Go. Okay. You all have chalks? Any questions?
Oh, no, I'm sure.
Okay.
the same shape of airfoil?
Have the same what?
Same shape of airfoil. We can can we assume the CL is the same for both?
Sure. In this question, it doesn't matter what airfoil they use.
I mean the CL, just the CL parts.
Oh, the CL are not going to be the same, right? Because they are not, even if there's the same airfoil, they may not be at the same angle of attack. If you look at an airplane, the wing and the horizontal tail, they are pitched differently.
I don't think in the normal case.
Yeah, sure, it's fine. But like the first question actually has nothing to do with aerodynamics.
Okay.
The first question is just the basic balance of moments.
Okay.
Yeah, the first question has nothing to do with aerodynamics, so it's just a balance of forces. Yeah.
By proportion of CL.
Yeah, just the ratio of lift coefficient, right? So here you have a ratio of lift. Also figure out the ratio of CL.
Oh, because we have the relative areas, right?
Yes, you have the relative areas. So 1 second. So why is this equal to 0?
Because your moment, you're in level flight, so would your moment around that be equal to 0? Because you're just
So what is this moment?
L1 times your 0.1.
And how about this?
Oh, 1.1.
1.1. Yeah. Yeah, that's a balance of force. You also need the balance of moments.
Ah.
Yeah. Yeah, the first question has nothing to do with aerodynamics. So the second question, you need this. The first question, you don't even need that. It's just the balance of force and moments. Yeah.
Do we need to take into account the moment that the wing produces also, or no? Because
Around what?
around its quarter chord?
No.
No.
Yeah, we're assuming the lift concentrates around the quarter chord, so that means no moments around the quarter chord.
And this has no. So never mind. Then. We'll do a moment about the. We can find the lift.
This is the balance of forces.
Like you have to choose a chord. So it's just we put it here. This one. Now this is 1. This is yeah. It's like there's no weights.
Yeah.
Because you're just doing.
Yeah, that also works. Yeah, that's right. That's right. But also make sure you understand the sign, right? The direction of the lifts. Yeah. Yeah, that's good. That's good. Yeah.
So we would do
It's negative, yes.
minus weight.
It has to be negative, otherwise the moments wouldn't balance.
Plus, it's like a ratio of the actual and actual is bigger.
Yeah, so
Can we just?
this is 0.1, this is 1.
Oh, okay.
My question
One
is,
from here to here.
Yeah, yeah, and 1 from here to here.
Okay.
But when we're doing the moments here, it's like if we put the center of the moment right here.
Okay.
This has a length of 0 essentially.
Yeah,
It's right
the
on.
gravity doesn't matter.
Exactly.
Only the two lifts matter.
Exactly. But at that point we can't balance the lifts because you just have 2 lifts that go up.
The two lifts doesn't have to go up, right? Like, who said that the lift has to go up? Lift is always orthogonal to the direction of free stream, but it doesn't have to be up or down.
Like this, we can just choose this, and then the math is going to tell us. What,
Yeah, the math is going to tell you the sign. Yeah.
Okay. So you could just designate the point right here and you can just take out weight in general.
Yeah, you can take out weight in general. Yeah.
Well, not for this, right?
Yeah, not for this, but for the moments.
Okay.
Sure. Okay. So this is the forces.
Yeah.
And then the moments. And then you can do it about this thing. So you can do 0.1 times L wing
Yeah.
plus 1.1
Yeah.
times L tail.
Yeah.
And now you have the system equation instead of
Yeah. Yeah. And you actually only need the second one because you need just the ratio of these two, right?
Oh, that's true. This is 0 because it's.
This is 0. Yeah.
Because
The area, I have to say. This is true. I mean, we know the relationship between them, right?
1 second. So where did this equation come from?
what's the same moment?
Around what? Yeah. So this is correct, but the lag of this is 1.1. Oh, sorry. Yeah, just to change your 10 to 11, that'll be correct.
This one's supposed to be teaching.
Yeah,
Question.
yeah,
So we were working it out, and we get this as like negative 11.
yeah, that's right.
It's a negative ratio.
It's a negative ratio. That means the horizontal tail is putting a downforce on the airplane.
Okay. Interesting. I don't know. It just seems weird.
It's always the case, like for balanced for airplane that is longitudinally stable.
Okay. I got you.
Because the acceleration is 0 of the plane.
Yeah.
And that's okay.
Yeah, as long as your center of gravity is ahead of the main wing, the tail has to provide a downforce.
That makes sense. Okay. And the moment with because you're going to have a reaction moment.
I think the states are always going to maintain the same proportion to each other.
Yeah, so this is already enough, right? What is m? What is the total moment? What does the total moment has to be for the airplane to not pitch up or down?
0.
0, yes.
Wait, but if you're statically stable, right, and you pitch up, and you want to pitch back down, like
But for level, so stability concerns if the airplane takes a small perturbation, right? Does it pitch back or pitch away from the equilibrium? So this problem still is only about the equilibrium. So starting from question 3, now you are talking about stability.
I think we're on question 3.
Oh, you're on question 3. Sorry. Yeah. So, okay. Oh, yeah. Okay. That's good. So you're trying to figure out this.
Yes.
And no, question 3 is looking at how does the proportion of first figure out how does the lift coefficient change.
Well, wouldn't they not change because you said like the increment of CL per increment and angle of attack is the same for each one?
This is the question to the. This is the second question, right?
Yeah.
So now, if each of these increases by the same amount, would this change or not? No, right?
Yeah.
Wait. So if this both, just imagine this is 11, this is 5. If both increases by 1, would it change? Well, actually, this is 11, this is minus 5. If they all increase by 1, this is 12, this is minus 4. This is going to change, right?
Oh, okay. Oh, okay.
Solve for like this would be L prime would be L1. And then L2. What? I'm reading that as LL.
So this is correct. What's your second? Oh yeah, that's also correct. Yeah. So you're on C, right? Okay.
Yeah, we're on the angle of attack.
Yeah. Okay. So if you're on question C, first figure out how does the proportion of CL change, and then figure out how does the proportion of lift change. Okay, so if you already have the ratio of CL, imagine both CL gets incremented by the same small amount. How does the ratio of CL change? Right, so here you figure out the ratio is this by this, right?
Yeah.
So just imagine, for example, well, this should be positive, this should be negative, right? So just imagine this is 11, this is 11, this is minus 5. I mean, it makes more sense to be saying this is 1.1, this is minus 0.5, okay? And if both increases by 0.1, how does 1.1 becomes? 1.1 becomes 1.2, right? How about minus 0.5? Minus 0.4, right? Yeah.
Why does both increase with the same amount?
Yeah, this is because we're assuming increment of CL per increment in angle of attack is the same for both the wing and the horizontal
Is this
stabilizer.
kind of like
talking about going like negative, going down?
Yes, negative means the horizontal stabilizer has to be providing a downforce.
Okay.
And question 3, you have to use the assumption that incrementing CL per incrementing angle of attack is the same for both wing and the horizontal stabilizer.
Something like this is currently like
Yeah, that's good. Oh, but so okay. So are both of these CL positive?
Wait, hang on. I think it's
Yeah, this one has to be negative, right? So when you pitch up, the positive is going to become even more positive. The negative is going to become less negative. All right. Yeah, this is good. Yeah.
So we're doing number 3.
Yeah.
And since we can assume that the change in angle of attack with respect to the CL is going to be the same for both
Yeah.
main and
Yeah,
so that means the CL would be the same.
Well,
So-
the area is 5 times more on the wing.
So this is the ratio of the lift coefficients, right?
Yes.
Just imagine for this one it's 1.1. For this one is minus 0.5. Okay. So if they both increases by 0.1, how does 1.1 become 1.2? Right. How about this?
Minus 0.4.
Minus 0.4. Will this change or not? This is going to change.
It's going to get positive.
It's going to become even more negative, actually, right?
Well, because this becomes negative 1.2
same thing as if you don't.
over.
No, this will become positive 1.2 over negative 0.4. The main wing is positive. I mean, the airplane wouldn't be flying if the main wing is negative.
But if it keeps going, like if it goes by 100, like this is going to keep decreasing.
Oh, well, I mean, at the point where the horizontal tail no longer provides downforce, the ratio is going to be infinity. I'm just, let's first figure out for a small change.
Sure. Okay.
Okay.
It would be.
Yeah?
So if we're changing,
Because this is going to get.
we're adding the alpha,
This is going
change, we found how CLW, I guess,
Okay.
changes, right?
One second. Are you looking at still 1, right? The CG ahead of the main wing, right? So let me see. So, I feel like there is a sign error somewhere.
No, this should be a minus right here for the
Yes,
sum of
yes,
forces.
that's
So this
right.
is 11 to 1.
Yes. Exactly. Okay, so just to change your 9 to 11, yeah, it should be fine.
so then this should be negative.
Yeah. Okay. Good.
The lift gets more and more here.
Okay. So another thing is that this is providing downforce, right? So if you increase the angle of attack for both, the positive force is going to get more positive. How about the downforce?
More negative, yeah. Less negative?
Same thing here.
So this provides negative lift, which means the horizontal stabilizer is going to be at negative angle of attack, right? So if you pitch up, the negative is going to become less negative. So another way to think about it is if you make it point up, right? So then the lift is going to be like a negative.
Negative 1.6 of this.
So essentially, as you pitch up, right, anything that provides negative lift is going to be less negative and eventually become positive. Right. So when you are looking at a delta, the delta actually have different signs.
Okay. Thanks.
So it's going to increase by.
Yeah, this is good. And
I think we're a little lost on what answer is.
yeah, so these are the same, right?
Yeah.
Okay. And so basically, the answer we're trying to find out is that is the change positive or negative?
This.
Yes.
It's just hard to describe it.
So basically, imagine this is a minus 0.5, this is 1.1, right?
Yeah.
If both increases by a small amount, let's say 0.1, 1.1 is going to become 1.2, right? How about this?
Okay.
Negative 1.4.
Yes, negative 0.4.
Yeah.
So the ratio is going to become smaller, right? Or going towards zero.
Oh yeah.
Yeah.
Absolute value smaller.
Yeah, yeah. Now let's figure out how about the ratio of the lift.
Okay, so okay, so you're not looking for like a numerical answer, just like a
Yes, yeah. Because I didn't give you a numerical value for this guy, right?
Yeah. Okay.
Yeah, for C and D, we're not looking for numerical answers. We're looking for directional answers, right? Does the ratio increase or decrease? And that is going to give you an answer to the D. Is the resulting moment positive or negative? Which way is the resulting moment? Yeah. Sorry, what's the question here?
We're just confused.
Yeah, this is correct. Okay, and so yeah, for question C, right? You're looking for a directional answer. So just imagine the lift coefficient here is 1.1. Lift coefficient here is downward 0.5. So if the airplane pitches up a little bit, let's say if the lift coefficient both increases by 0.1, so 1.1 is going to become 1.2. How about this one? 0.4, right? Because it's downward, increasing the angle of attack is going to decrease how much downforce. So the ratio, yeah, the ratio would become bigger. That's right. Depending on what direction you, I mean, if you are saying the CL is downward CL for the vertical for the horizontal tail, then this is not negative. If you define it to be always in this direction, then it's negative. So it's up to you.
The plane itself goes up.
Just to make sure it's consistent.
The wing goes up. The angle of attack.
So then this just
The
gets bigger?
magnitude of it
Yeah, ratio increases. That's correct.
Okay.
goes down.
Cheat question.
Yeah.
And, we were thinking, like, since it's like lift is proportional to the coefficient of lift times area, it was almost like it would be this plus the change in that coefficient of lift over area times the area.
Yep.
And this is 1/5 of the area of the other thing.
Yep.
So that would be the change in the moment, the numerical approach to D. Right? Or
Yeah, that can also work.
sure. But
Yeah,
intuitively, I
it's-
guess it's like this is getting bigger.
Yeah.
This is getting smaller, right?
This is getting.
Or like this contribution.
The angle of attack.
Yeah. As we increase the angle of attack, this contribution becomes larger.
Yeah.
This contribution becomes smaller.
By smaller, you mean closer to zero?
Yes.
Yes.
Closer to zero.
Okay. Yeah.
Okay.
Yeah. That's right.
Oh yeah, so I guess it's bigger.
And so it's gonna be, yeah. I don't know how to describe that like intuitively. It's just like this is the wing makes more of a contribution than.
That's
tail.
right. That's right.
Okay. That's it.
Yeah.
Okay.
Yeah. That's right.
The wing will contribute more to the moment. That's basically.
Yeah.
that's right.
The wing almost takes over the moment.
Yes,
As
yes.
we go over, we see that this turn.
The wing takes over more.
Yeah.
Yeah.
And then, yeah, as DCL goes to very, very high numbers, it eventually just goes to infinity with like
Yeah.
a contribution.
Yeah. That's right. That's right. So how about D?
Wait, that's D, right?
No. What is the resulting moment around the CG?
It would be the opposite.
Just to draw an angle. Like draw. Like what is the moment?
Oh, like the.
Zero moment. So it would be.
No.
The other way.
Like
right?
you're saying the lift. So the lift on the main wing goes like that. The lift on the tail goes like that, right? Yeah. So if the wing now dominates, it should be like that, right?
Yeah.
Okay. And does it pitch the airplane up or down?
It goes up like that.
Well, actually,
The
no,
moment.
it goes down.
Yeah. It pitches down, right? I mean, it lifts the airplane up, but simultaneously it pitches the airplane down. So there is a difference between like the acceleration and angular acceleration,
Sure.
right? I mean, if you look at the total lift, it increases, which means the airplane is going to float up, but at the same time it pitches down
Because this whole thing.
because of the moment, right? Yeah.
Oh,
So the angular acceleration is nose down, but the directional acceleration is translational acceleration is upwards.
That's why we need tails.
I don't know. Oh, it's just that you can put one. Never mind. We figured it out. Wait, for like the unstable case.
Yes.
L1 over L2 is positive.
Yes, exactly. Yes.
Yeah. 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 Okay.
Wait, would it have to be the thing?
5, and then small increment. Well, the small increment means this will get bigger, and this will get smaller. This will get bigger, this will get smaller.
Yeah, you need to just be consistent in the direction, right? So if you define the lift on the horizontal tail to be upward the lift, then this is going to be positive. If you define it to be negative direction, then it will be negative. So it's up to you. Just to be consistent. Make sure you define the direction and stick with it. How's it going here?
It's going good. Working on part D.
Okay. So what's the answer to part C?
We got for a given like CL naught increment of both sides, you get like the proportion of the difference of CL is 6 over 11.
So it's pretty.
Okay, so this is correct. And how did you do this one again?
So we added like a CL naught increment to both CL and CLH.
Yeah.
And then we substituted the equation for CL into here. And then solved for the change, which is 6 over 11 CL naught. And then just divided this expression by like delta CL, which is just CL naught.
Yeah. So
6 over 11.
So for question B, the ratio, the answer is what? -5 over 11. Right?
Yes.
Okay. And for the answer to this, the question is, does it increase or decrease? Does this ratio increase or decrease? Is it going to get closer to 0 or further away from 0, more negative?
Oh. It should be more positive, right?
So just imagine like -5 over 11, right? So imagine the CL of the tail is -0.5, CL of the main wing is plus 1.1. So if you pitch up, let's say the 1.1 becomes 1.2.
Yeah.
How does the minus 0.5 become?
Sorry, a minus 0.4.
Minus 0.4, right? So now what is the new ratio?
Negative. What? Yeah.
Negative 0.4 divided by 1.2, right? Yeah.
So like 1/3.
So it gets closer to 0 or away from 0?
It gets closer to 0.
Closer to 0, yes. Right. So that's the answer to question C.
Okay.
Now, okay, so that's the question to the ratio of CL. How does that tell you about the ratio of lift?
Well, the difference would be the S, like the reference area.
Yeah. So does it also get closer to 0 or not?
No.
Yeah. The ratio of lift is the ratio of CL times the ratio of wing area.
Yeah.
Right.
Yeah.
The ratio of wing area is fixed.
Right.
So if the ratio of CL gets closer to 0, then the ratio of lift also gets closer to 0.
Okay. Yeah. That makes sense.
Yeah. So that's C. Now that answer should help you figure out D. Right.
Okay.
Like basically look at the balance of moments again.
Okay.
Now you know the ratio of lift that gets closer to 0.
Somebody.
Interesting.
How are we doing here?
What?
We're starting the second one.
We're gonna do number 2.
Oh, okay. So finish the number 1.
Yeah.
Okay.
Yeah.
Okay. Good. So
Not sure
what's
if it's
the
done
answer?
correct.
What's the answer for?
Like
It was less negative.
Less negative, yeah. So getting closer to zero, right? So what is the resulting moment?
It was 1/2 rho v squared times 0.
Well, so I just want the direction. Does it?
It goes like this.
Nose down, right?
Yeah.
Yeah. So basically, you're gonna get the translational acceleration upwards, but the rotational acceleration nose down.
So true.
Wait,
Yeah.
can you say it again?
So because because the lift in the main wing increases, the downforce on the tail decreases.
Yeah.
So the resulting total force is going to be more than the gravitational force, right? Which didn't change. So you are going to get a total force upwards. So the airplane is going to be accelerated upwards, but that's linear acceleration. You also get the angular acceleration. That has to be determined by that moment.
Yeah.
And that moment is nose down. So it's going to be accelerate upwards, but nose down. Yeah. Okay.
We're a little bit confused.
Yeah. So.
How our proportions changed, I don't know what.
Oh, okay. So the best way to do that is you're on question 1 or 2.
1.
1. Okay. So the best way to do that is so assuming this is 1.1, this is minus 0.5. So if they both increases by a little bit, let's say 1.1, 0.1. So the 1.1. Yeah, that's right. So
Then I think for the lift proportion, we didn't know how that would change.
oh, okay. So is this so does this ratio get closer to 0 or further away from 0? Further away, yes, right. Okay, so the ratio of lift, where is your ratio of lift? So the ratio of lift is equal to the ratio of CL times the ratio of area.
Oh, I think that's what we tried to do here.
Yes, and if this gets further away from 0, how about this? That would also get further away from 0, exactly. Right? So that's the total answer for C. Both are going to get further away from 0.
Oh, okay. But then like a written numerical sense.
Yeah, so written basically, if this guy, well, it's negative, so this guy decreases, right? Gets closer to minus infinity. This has to also decrease, right? And the amount of decrease is 5 times as large as the amount of decrease in this one.
Oh, okay.
Right.
Fine. Okay.
So for our moment part, are we doing like that similar thing of like just the sum moment of the lift?
Yes.
You said it went nose down. So.
Yes, and basically this is you can do this. Okay, so can I? Okay, so you can take this as 0.1, right? Times 0.1 times the original lift of the wing, right? Plus a ratio of 0.1 to 1.1 times the lift of the horizontal tail, right? Right. And the ratio of these two LT is actually exactly equal to 1.1 over actually negative initially, right? Okay, so you can also write this as 0.1 times the lift. It's actually 0.1 times lift of the wing times 1 plus 1.1 over 0.1 times lift of the tail over lift of the wing, right?
Yeah.
Actually, you did it this way, so let me actually erase this and put it the other way.
Okay.
So this is equal to 0.1 times lift of the wing divided by lift of the tail, right? Plus 1.1 over 0.1. The whole thing times the lift of the tail. Okay, so this guy before the pitching up was exactly negative of this guy. Now this gets even more negative. So the total moment now becomes negative, right? because initially this is exactly 0, right? This is negative of this, and this is this. That's yeah. Then if this gets more negative, this is going to be total as negative. Yeah, sure.
Yeah, we got that like it was a positive moment this way. So
Yeah.
just do a backflip.
Yeah, that's right. Okay, so I think all of you have gotten the answer to question 1, right? Anybody are still working on question 1? It doesn't matter if you are working on question 2, because the answer, I mean, if you figure out question 1, it's just a different calculations, right, to get the answer to question 2. So anybody are still working on question 1? No? Okay, so let's come back, and I'll just give the answer. So for question 1, the proportion of the main wing to the horizontal tail, if we define upwards as the direction of lift, which means a downforce would be negative lift, the ratio is going to be 11 to 1, and it's minus, right? I mean, this is basically from a balance of moments. And the proportion of lift coefficient is equal to the proportion of lift divided by the proportion of area. So I can just divide this by 5, which is the ratio of area, to get the proportion of lift. Now, to get question 3, just imagine the proportion of lift is 1.1 over minus 0.5. So imagine the main wing has a lift coefficient of 1.1, the horizontal tail has a lift coefficient of minus 0.5. So if 1.1 increases to be 1.2 when the whole airplane pitches up, minus 0.5 goes to minus 0.4, right? Less downforce if the horizontal tail gets a less negative angle of attack. The proportion would go from minus 11 over 5 to minus 12 over 4, which means the ratio gets even more negative, right? Okay, and so basically the CL wing over CL tail decreases, and the lift of the wing over lift of the tail is just equal to 5 times CL of wing over CL of tail. If the ratio of CL decreases, the lift of the ratio of lift also would decrease, also gets more and more negative, right? I mean, for those of you who did the ratio backwards, it would be getting closer to 0. I mean, either way, it means the same. Okay, what is the resulting moment around the CG? You can do it numerically, or you can do it intuitively. So let me just do it numerically over here. So the total moment is equal to 0.1. Let me define the moment as moment counterclockwise, right? Then the wing is going to be providing a positive, actually, if I define it that way, the positive lift on both surfaces are going to give positive moments. So the total moment would be 0.1 times the lift on the wing plus 1.1 times the lift on the tail. Okay, which, if I use this ratio, would be 0.1 times the lift on the tail. The first part is going to be multiplied by lift on the tail over lift on the wing over lift on the tail. The second part is going to be plus 1.1 over 0.1, right? Okay, so the ratio initially, as you see, the ratio initially is minus 11. So, which means this number initially, without the changing angle of attack, is going to be exactly 0, right? This is plus 11, this is minus 11. Okay, now this number gets closer to minus infinity. It decreases, right? Which means this number, instead of being 0, is going to be negative. Okay, a negative moment in this direction. 1 second, did I do something wrong here? lift on the wing. Oh, okay. Sorry. Yes. So what is in the parentheses is going to become more negative, and but the lift on the tail is actually negative. So it's going to be multiplied by a negative number, and this is positive, right? I got myself confused. So the lift on the tail is a negative number, and the LW over LT is going to become less than minus 11. Right, which means this parenthesis, this something less than minus 11 plus 11 is going to be negative. That negative parenthesis multiplied by this negative lift on the tail is going to get you something positive, which means the airplane is going to have a positive moment in this direction, in the nose down direction. Okay, and so if you look at the airplane is going to have an increased angle of attack. It's going to have an increased lift. As a result, the lift summed up is going to be more than the weight. It's going to have a linear acceleration upward. But at the same time, what is the angular acceleration? The angular acceleration is determined by the moment, which is going to be nose down, right? So the plane has a linear acceleration upward, but the nose down angular acceleration. All right, and we actually have the opposite result if the CG is behind the main wing, right? So as you have a positive gust, the airplane is both going to have a positive linear acceleration and a nose up angular acceleration. So that's a unstable scenario where nose up is going to get you even more angle of attack, and as a result, even more nose up, etc., etc. So this is a good design. This is a design that requires some kind of a very high frequency control system to be able to fly. All right. Okay. So yeah. So let's come back on Friday to discuss dihedral, which relates to lateral stability.